Besides explicit formulas, we also have something called a recursive formula, which helps us define a sequence. And the quickest way to define a recursive formula will be with an example. So the Fibonacci sequence is a very famous sequence. You've probably heard of it somewhere, which is defined recursively. And it's defined recursively because we've got a couple of terms. So the first few terms are defined just straight out, give me the numbers. And then future terms, and it doesn't have to be 2 terms, it could be 3 terms, or it could just be 1 term. You have to have at least one though. And then once you have that, future terms are going to be defined by previous terms. And if you have this set up where you are told the first few terms are the first term, and then all the future terms are defined with a formula involving the previous terms, that's called a recursive formula. Okay, so it says write the first 10 terms of the Fibonacci sequence. So I'll go ahead and rewrite F0 is 1, F1 is 1. So how the heck am I going to figure out what F2 is? Well, I've got to use this formula that tells me how to define future terms. And let's see, I know what Fn plus 2 is. So what I'm going to do is I'm going to replace that n with a 0. F0 plus 2. And that tells me that I want F0 plus F0 plus 1. Of course, F0 plus 1 is just F1. This is just a really fancy way of saying that each term is the sum of the 2 previous terms. That's all I'm really saying there. So yeah, that means we got F0 is 1, F1 is 1, 1 plus 1 is 2. All right, so again, I could do it the long way where F3 is, well, I just change that 0 to a 1, 1 plus 2. This formula says where n is equal to 1, I got F1 plus F1 plus 1. So that's F1 plus F2. But again, that's just a really fancy way of saying that F3 is the 2 previous terms added together. And hey, I've got a 1 and I've got a 2. 1 plus 2 is 3. All right, so basically we can see here that this recursive formula just adds up the 2 previous terms. So let's keep going. F4 should be 2 plus 3. That's F2 plus F3 is 2 plus 3 is 5. And then F5 would be 3 plus 5 is 8. And then you can kind of see the pattern here. So let's just go ahead and start writing them out. We got 1, 1, 2, 3, 5, 8. And then let's see what comes next. The next thing here would be 5 plus 8 is 13. The next one would be, let's see, 8 plus 13 is 21. How many terms do I got? 1, 2, 3, 4, 5, 6, 7, 8. I need 2 more. 13 plus 21 is 34. And then the last one I'm going to write is 55. 21 plus 34 is 55. All right, so there are my first 10 terms of the Fibonacci sequence. We could do this forever, of course, but we don't have time or the patience for that. Let's do another example instead. Okay, so for this example, we're asked to write the first 6 terms of the factorial sequence, and that we're given a formula for that. Now you might be familiar with another formula for the factorial sequence, and note that it's usually written as n factorial rather than exclamation point sub n, but I wrote it like this just for this problem because to remind us that this actually is a sequence, and we can write it sort of like we do other sequences, even though we usually will not. But let's go ahead and do it. So I've got what we call 0 factorial is 1. All right, if I want to figure out what 1 factorial is, so let's write it both ways. 0 factorial, 1 factorial, and let's see, what would that be? Well, this says we should take, so we have the subscript, we should take that subscript and rewrite it. Okay, and then if this is n plus 1, n would be the previous one. So this would be factorial times 0, or I could just say 0 factorial, and that is also 1, and that gets me, of course, 1. So 0 factorial is 1, 1 factorial is 1, 2 factorial. Let's see, we need to take the subscript 2 and then rewrite it, so we get 2 times 1 factorial is the previous factorial, and that's going to be 2 times 1 factorial is 1, and that's 2. 3 factorial, again, we usually write it this way. All this says is we're going to take 3 and multiply it against 2 factorial, the previous term, and that's going to be 3 times, well, 2 is 6. 4 factorial is 4 times 3 factorial. That's 4 times 6 is 24. It says write the first 6 terms, so this will be the last one, since I started with the 0 term. 5 factorial is 5 times 4 factorial. That's 5 times 24 is 120. All right, so I can list them all out together. 1, 1, 2, 6, 24, 120. There's the first 6 terms of the sequence. Now, if you're familiar with factorials, you might be familiar with sort of an explicit formula. It's actually impossible to write an explicit formula because you don't know how many terms. We can kind of fake it. So what do I mean by all that? Well, it's no longer part of the problem, but here is an explicit formula. Notice that your n factorial is just taking all the numbers. So let's just split up 5 factorial. 5 factorial equals 5 times 4 factorial. 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial. 2 factorial is 2 times 1 factorial. And 1 factorial is 1 times 0 factorial. And 0 factorial we define at the very beginning just to be the number 1. Basically, we think of that as 0 things being multiplied. All right, and there it is. So the explicit formula, here's an example. So it's not hard to see that n factorial is often just described as n times n minus 1 times, keep on going until eventually you get down to 3, 2, and 1. It's the first n numbers multiplied together. All right, let's take a look at one last example. So we're going to prove that this particular explicit formula matches a recursive formula. And because sequences could be described, whether it's described with an explicit formula or we can define it with a recursive formula. So let's take a look at this one. What is the sequence? That actually won't help me solve the problem, but it might be interesting to just note that if we have A0 is 3, and then A1 says, let's take the previous term, n plus 1 comes right after n, so take A0 and divide it by 2. There's going to be 3 halves. A2 says take A1, divide it by 2. 3 halves divided by 2 is 3/4. So A3 would be 3/8, then 3/16. And of course, if we could use that same formula up here, A0 would be 3 over 2 to the 0. 3 divided by 1 is 3. A1, so this is using the recursive. This is using explicit. A1 would be 3 divided by 2 to the 1 is 3 halves. 3 divided by 2 squared is 3 fourths. 3 divided by 2 cubed is 3 eighths. And we can see how they're matching up. Here, 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 here. Let's go ahead and write A4 is 3 divided by 2 to the 4th is 3 sixteenths, so on and so forth. So they do seem to match up, but I put this in parentheses because it doesn't prove anything. How do we know they don't become different like at 10 or 7 or 120? You know, I could just make up a big number, a million. They might be different in a million. I don't have time to check all that. So in order to prove that they're compatible formulas, here's what we need to do. We just need to take this formula and make sure that it fits both of these criteria. Okay, so here's the proof. All right, A0 should equal 3 divided by 2 to the 0, and that should equal 3. And 3 divided by 1 is 3. So that checks out. So that certainly works. This explicit formula matches A0 equals 3. The next step is to show, so let me write this out. So we have to show that A0 equals 3. All right, now we need to show that AN plus 1 equals AN divided by 2. Okay, so AN plus 1 equals, according to the explicit formula, 3 over 2 to the n plus 1 okay, and then I'll just leave it like that, okay, and then I also have AN divided by 2, and according to the formula that's 3 divided by 2 to the n divided by 2. But what is that? That's 3 over 2 to the n times, flip the denominator, 1/2, 3 over 2n times 2, that is 3 over 2 to the n plus 1, and they match. And that checks out. So both, this formula satisfies both of the recursive requirements, and therefore that completes the proof for us right there.